So we've been graphing these polynomials for like 2 days or whatever. And, oops, that's too, there we go, that's perfect. So let's talk about what we've kind of figured out by just graphing these. Okay, so it says, what determines how many x-intercepts of the graph a polynomial function in intercept form has? So how do we figure out how many x-intercepts there were? Well, we graphed it, but just based on the function. In other words, if I wrote a function like f of x is equal to x plus 1 times the quantity x plus 2 times the quantity x minus 3 times the quantity x minus 4, how many x-intercepts would there be? 4, right? 4 intercepts. So the way that we determine that is what? What do we call those things that I just wrote down? Huh? Distinct factors. So you will put the number of distinct factors equals x intercepts. And I'm abbreviating the sentence a little bit so it fits. Right, so if I have 4 distinct factors, right, I have 4 intercepts, so I'm going to put over here 4 distinct factors. I have 4 x-intercepts, because those are the zeros. Nah, that looks bad. Those are the zeros. All right, it says, what determines whether the graph of a polynomial in intercept form crosses the x-axis or tangent to the x-intercept? Tangent intercepts have even multiplicities. Now, multiplicity means solutions. So if I say f of x equals x plus 2 squared times x minus 1, x equals negative 2 is a solution. Multiplicity of 2. Because when I factor this, it'll be x plus 2, which is a solution, times the quantity x plus 2, which is also a solution, which is multiplied by x minus 1. In other words, the solutions will be x equals minus 2 and x equals minus 2 algebraically when I solve it. And x equals positive 1. So if I take all 3 of these and set them equal to 0 and solve, then what I'm going to end up with is the same solution twice. And on some of these polynomials, you'll end up with the same solution 4 times, or 5 times, or 3 times. If the multiplicity is an even number, then it's tangent to the x-axis. It touches it, but it doesn't cross. All other intercepts will cross. I suppose if you want to tell yourself if it's a odd multiplicity, it'll cross. That's true. And so x equals 1 is a multiplicity of 1, which is an odd number, which means it'll cross. Does that make sense? And then it says, suppose you introduce a factor of -1 into each of the quartic functions in step B. And so what they mean by quartic, everything in our last page was fourth degree polynomials, and so they call those quartic, like quarter, like 4. What does that negative do? And how does it affect the graph? It just flips the graph. And you could put in there the y values. It just negates the y values. It makes them the opposite. Flips the graph over the x-axis. But then think about, what does that do to the mins and max? Well, then the mins become maximums, and the maxes become minimums, right? So what they're saying is, watch what happens. This graph, right now I have 2 minimums, right? 2 minimums, 1 maximum. If I go in here, and in the beginning, I put a negative symbol like this, watch what happens. Boop. Now I've got to adjust my screen, but you see now I have 2 maximums and 1 minimum. And all I did was flip it. That's it. Does that make sense? I mean, it changes the end behavior and all that stuff. But what we're focusing on are those minimums and maximums. And that just reminded me of something. I'm going to go back here real quick. We talked about 2 local minimums. I really probably shouldn't use the word local for both of those. I probably should say I have 2 minimums, right? One is a global minimum, and then the other one is a local. So this one is a local. By moving that word local from here to here. Because you can have minimums and you can have maximums, but you have to distinguish between minimum, like whether it's local or global. After I thought about it, I'm trying to think of a way to help you identify the minimum and maximum, but we still do technically. It's very important to label them correctly. I don't know why I do that silly stuff. So now let's see if we could graph this kind of in our head, and then we'll actually graph it. So this is a third degree polynomial. I have 1, 2, 3 x's. So somewhere I'm going to have x to the third power. That's an odd power, and so it's going to start here and come out here, right? We remember that the odd powers look like this. If the leading coefficient is positive, do you see any negatives? No. If the leading coefficient is positive, it kind of comes in from the bottom and goes out like that. So I know it's going to have this kind of shape. So then the next thing I need to do is figure out how many distinct factors I have. Well, I have 3 distinct factors. So at most, 2 turning points. I might only have 1 turning point. I might not have a turning point at all. I can't write with this stupid thing. Okay. All right, cool. So what are the zeros? Well, I'll do the first one, x equals 0. You guys do these. X plus 2 equals 0, and x minus 3 equals 0. I'm just taking the factors and solving them. What's this one going to be? X equals what? We're not doing the graph. We're going to do the graph by hand. Negative 2, good. What about this one? X equals what? 3. Now these are the x-intercepts, right? Do I have any of those solutions written down more than once? No. So I don't have any even multiplicity, so all these cross. In other words, I'm going to cross at x equals negative 2. I'm going to cross at x equals 0, and then I'm going to cross also at x equals 3. Okay? Now, based on that, I should be able to loosely identify that this will probably do something like this. That's a sketch. It's not perfect. Okay? Let's graph it, real deals. See what we get. So let's come in here and I'm going to clear this out, and I'm going to say x times the quantity x plus 2, plus 2, times the quantity x minus 3. I'm going to hit zoom standard, and hopefully the whole thing will fit. Not too shabby. Let me make that big, and we'll take a screenshot. Now, if you had data that you needed to model that on, it would just be a matter of fine-tuning, right? You could just change some of these numbers around to make it fit the way you want it to. Let me see how accurate my graph is if I put it right on top of this one. I just need to make it a little bigger. Oh, a little bigger. Not too shabby, right? Close enough. I think I'm just going to leave it like that. No. So you could see that my little graph that I kind of sketched eyeballing it and the actual graph are not that far off. And that's what we're trying to do. How did I know it would come in from the bottom? It was an odd power. How did I know it would cross the x-axis? Multiplicity of 1, so on and so forth. Okay? Do you guys have that written down? Can I move on to the next example? Okay. Well, I need to copy the next example in order for us to do it. Trying to find one with a multiplicity that we could do. They just don't do a really good multiplicity. I'm going to make one up. We'll make one up real quick and just see what it looks like, okay? So I'm going to say f of x is equal to x minus 1 squared times the quantity x plus 2 times the quantity x minus 3. Okay? Now, I'm going to go kind of quickly on this one because we're going to run out of time. What time do we get out of here? 47. All right, we gotta go quick. I've got an x here, but really I have two of them, and then I have x's here. So I think I have a fifth-degree polynomial, but immediately I'm going to write this as x minus 1 times x minus 1. That's what that means to square that, right? So I have 4 distinct factors. So we're going to say 4 factors, 4 distinct factors. Okay. So at most I'll have 3 turning points. And it's x to the 4th power, which means it's an even power. Leading coefficient is positive. So if I were to graph this, it's probably gonna do one of these things. It's gonna come in from the top, do some stuff in the middle, and then go out the top, right? Do you guys see that? It's gonna come in from the top and kind of do this thing. Yes. Because it's an even power. Now the other thing I need to do is find the zeros. So to find the zeros, and this is, I got to go quickly, I'm going to say x minus 1 equals 0. That's the first distinct factor. X minus 1, actually it has 3 distinct factors, I should say that. It has 3 distinct factors because I'm listing one twice. And so it'll probably only have 2 turns. So let me, because it's based on the distinct factors. So 3 distinct factors probably has 2 turns. And we're guessing equals 1, and then, or equals 0, and then x plus 2 equals 0, x plus 3 equals 0. So then my zeros are going to be x equals positive 1, x equals positive 1, x equals negative 2, and x equals, sorry, I miswrote this down. This should be negative 3, which means my solution would be positive 3. So I'm going to cross at negative 2, and then at 1, well, these are my intercepts, and then again at 3. Now I know that this is going to come down, and I'll have to have 1 turning point. But this is multiplicity 2, correct? So it's not going to cross. What it's going to do is it's going to touch right here and turn right back around. And I'm going to get this W shape. Huh? How many solutions do I have for negative 2? Like, how many times is that written down? 1 time. So this crosses. Yeah, this one will cross. And this is twice, so this will be tangent. Remember? So it's going to come down through here. I'm going to turn around this way. I'm going to touch, and then go up that way. Let's graph it and see. You ready? I'm trying to hurry to beat the clock. Let me move this over here. We've got y equals, clear, y equals x, minus 1, subtract 1, raised to the 2nd power, times the quantity x plus 2, times the quantity x minus 3, close the graph it, and we'll zoom out a little bit. And so this is what it looks like. Does that make sense? That's it. That's all I was trying to teach you guys. Let's take a screenshot of that. The bell's going to ring any second. When the bell rings, just go ahead and, take off, go to your next class, learn lots of stuff. That's it.